Good morning, everyone. I'm Sarita Swanepoel, and this is the Junior Tukkie Summer School. And we are going to look at Newton's laws today. Now, if you want to work with us, you really need to have the study material printed out and ready so that you can work with me on it. Now, when we look at Newton's laws are all laws about motion, right? So they're all talking about motion. And that the motion depends on the forces working on that object. So now we need to consider forces. First thing you need to remember is a force is a vector, right? And that means it's got magnitude and it's got direction. And because it's got magnitude and direction, you can represent it with an arrow. The length of the arrow is going to give an indication of the magnitude and obviously the direction you can see from the arrow. But it's very important that you know that in maths and in science, we measure the angles differently. If you are working in maths and I give you a vector like this and I ask you in what direction, right, you will measure from the positive x-axis in the anti-clockwise direction and you will give me that angle, right? If we're working in science, now actually in science you can do one or two things. You can look things from the side and then we're going to work from horizontal or from vertical, right? But when we are looking from the top, we are going to talk about north and south and east and west, and then when I ask you the direction of that, we measure from north clockwise. So then you need that angle. So just remember, for maths and science, we are going to do things different. Right. Now, when you're working with forces, there's two very important things. And the first thing is to be able to get the resultant of a number of forces. If you've got a number of forces working on an object and you want to know where that object is going to move and how it's going to move, then it's very difficult to work with a lot of different ones. So what we're going to do is we're going to get the resultant. That is the single force, right, whose effect is exactly the same as all those individual forces acting together. And to do that, we are going to use either the head-to-tail or the tail-to-tail method, right? Now, with head-to-tail, if you look at this one over there, you will see we draw them one after the other. So you draw the magnitude and direction and then the other one. And then what's very important is you need to know how to get the resultant. And here, the resultant starts where the first vector starts and ends where the last vector ends. So if you look at this diagram, the first one starts over here and the last one ends over there. So there you've got your resultant force. Next up, tail to tail. Now, if you look at this one, you will see over there they've drawn from the same point. So we have the tail of the one and the tail of the other together. So what do I do if I've got tail to tail? I need to complete the parallelogram, and I do that by taking this force, right? The easiest way is to do this with your ruler, right? To take this force, keep the direction and the length the same, and repeat it on the other side. For this one, get the direction and the length and repeat on the other side. And then you get the diagonal of that, and the diagonal is going to be your resultant force. Right, so to see if you are happy and comfortable with this, let's move down to the bottom of the page where you have question 1. Now in question 1, I know it sounds easy, but really I have to do this basics first. Indicate the method of addition and then draw the resultant vector. So you have to say, is it this head to tail or a tail to tail? And then you have to draw in the resultant as well. And remember to label it. Now this is where you have to pause the video, do the question, and then come back to see if you've got it right. Now I hope all of you have done this. First one, if you look over there, you will see tail to tail, right? So tail to tail. And for tail to tail, up there we said tail to tail, we have to complete the parallelogram and then the resultant will be the diagonal. So let's complete the parallelogram. So I'm going to use my ruler and I'm just going to take that one and repeat on the other side, and take that one and repeat on the other side. Right, and then the diagonal of that will be the resultant. Now for a vector, we usually use a little line above the vector to indicate that it's a vector, but if you look at the Department of Education information sheet, you will see they haven't included that, so it's not necessary. Right, next up, if you look at this one, over there you will see this is head to tail. And for head to tail, the resultant starts where the first vector starts and ends where the last one ends. So the resultant is over there, and remember to have an arrow, otherwise it's not a vector, it doesn't have direction. Right, here once again, if you look there, you will see tail and tail, so this is tail to tail. And for tail to tail, I need to complete the parallelogram. So I'm taking this one, repeating on the other side. I'm taking this one and repeating on the other side. And then the resultant is the single one that is the diagonal. Right, so there I've got my resultant. Next up, we're going to look at the components. Now this is actually the reverse of what we've done now. Here we have two forces and we add them together to get the single one that has the same effect. Right, now we are going to take a single one and split it up into two, and we call them components, and they have to be perpendicular to each other, and they give the original one when combined. Right, so when do I use components? Now, one place that you will use components is when you've got a horizontal plane and you are moving an object by exerting a force not in the horizontal but in another direction. Now, if I'm pulling in that direction, this crate is not going to move in that direction. This crate is going to move in this direction. So that force over there is actually not giving us good information about this movement. So what I like to do is the opposite of what we do with the resultant. With the resultant, we took separate forces and made them into one. Now I'm going to take one and make it into two separate ones. And once again, I can use head to tail or tail to tail. So I can use head to tail and replace this with an fx and an fy. Right, you need two perpendicular to each other. Right, and what's important is we are now replacing that one with fx and fy. Together they do exactly the same as the original one, but now I've got a force telling me what's going to happen to the motion of this object, and the other one is perpendicular to the movement, so it's not influencing the movement directly. Right, so this was if we did it head to tail, but you can also make your drawing tail to tail. Now remember, with tail to tail, that force that we are splitting up into separate ones is the diagonal of the parallelogram. So we're working back to the parallelogram. So you will take that one and you will take that one and work back to the sides of the parallelogram. So we are replacing that f with an fx and an fy. Now guys, we do this because fx is now going to tell us how this object is going to move, and fy is not influencing that movement, not directly. Right, so how can I calculate this? Now usually we have that angle with the horizontal, and then if I look in that triangle, I will see fx is now adjacent, right? It's adjacent to that angle. Fy is opposite, and the original force is now the hypotenuse. Also in this one, adjacent, right, next to opposite, right, and that, remember, that opposite one is just the repeat of fy. So you had fy over here, but fy is over there as well, and f the hypotenuse. And then if we look at this, we can say, okay, so if we look at this and we say I want to work out fx, then we can work with the adjacent and the hypotenuse, and I will have cos theta being fx divided by the whole f, right? And that ends up with being fx is the whole force times cos of that bottom angle. Or if I do the same thing and I now use opposite over hypotenuse, I will have sine theta being Fy over F and end up with Fy being the whole force F times sine of that angle. Right, but remember we worked with the angle with the horizontal. Right, now when you are doing this in a question, it will be not even a half a mark, right? This is going to be a small part of a much bigger thing. If we do Newton's laws, for Newton's laws, right, say for instance we're doing a Newton 2 problem, you need the frictional force, right? And to get the frictional force, you need the normal force. And to get the normal force, you need to work out the components. So the components on its own will not even be worth a mark. They give 1 mark for working out the frictional force. So guys, this is going to be a very small part of the rest, but an important part. And you don't have a lot of time in every new question to decide, is x going to be cos or it's going to be sine? So what you have to remember is x will always be cos and y will always be sine if you are using the angle with the horizontal, because then you don't have to rethink every question because you don't have the time, right? This is not even a whole mark, it's just part of a mark. Right, moving on, let's make this more difficult. Now let's put this on an inclined plane. Right, let's say we've got an inclined plane with an angle of 30 there, and you've got your object there, right? And now what's happening to that object? Now let's think about the forces on that object. Now usually when you try to pull something up an inclined plane, you are going to exert a force or apply a force in that direction. So here F is not a problem. It is in the direction of movement, right? So this will give us good information about movement. What other forces are there? Now there's a normal force. We haven't talked about normal force yet. We'll talk about that in the next video, but it's always perpendicular to the surface, so that will not be influencing the movement. And then obviously you have gravity, and there you have the problem. Gravity is working straight down, so that is not in the direction of movement, so we don't know how it is going to influence the movement. So what we're going to do is we're going to replace that gravity with 2 components that will give me the information that I need. So let's say we stay with tail to tail. Tail to tail, I'm working from the parallelogram back to get the 2 forces, and I choose them. This component parallel, because that's going to tell me about the movement, right? And the other one, FG, perpendicular, because that is not going to influence directly the movement, right? So if you look at this one, we now have F gravity parallel and F gravity perpendicular. Don't want an X and Y again, because then you get confused with the horizontal surface, right? So we're looking at parallel and perpendicular. Now we have to work out the value, the magnitude of each of those. So for this, let's say this is a 30-degree angle. If you were to lengthen that, extend it right down, you will see that is a 90-degree angle. So in a triangle, all angles together should be 180. So that is a 60-degree angle, right? So it's the rest of that 90. Okay, and then once again, if you think about that one together, they are 90. So this one is 30 as well. So what you can remember, that angle is always and ever going to be exactly the same as this angle, right? And that will help us in that we don't have to redo it in future, right? We will just remember that one and that one is equal. So let's talk about this. If I'm working in this triangle, remember FG parallel is just repeated on this side. So this one is also FG parallel, right? So if I'm working the 30, that adjacent one is the perpendicular one, and the opposite one is gravity parallel. And now the hypotenuse is the gravity on its own. So if I look at this one and I say cos theta, right, cos theta being adjacent over hypotenuse, that will be FG perpendicular over FG, and then I end up with the perpendicular one always being the whole gravity times cos of that angle, and once again that angle is with the horizontal, right? And the same way I will say sine theta will be the parallel one divided by the whole gravity hypotenuse, and then I end up with the parallel one being the whole gravity times sine theta. Right, so now once again, no time in future to rework this, to rethink this. You just have to know the perpendicular one is always going to be cos and the parallel one is always going to be sine, and I just have to check that I've got the angle with the horizontal. Right, so on that first page, you will see this summarized down there, right? If you're on a horizontal plane, the x component is always cos and the y component is always sine if you've got the angle relative to the horizontal. And on the inclined plane, the perpendicular one will always be cos and the parallel one will be sine if you've got the angle with the horizontal. So then you don't have to rethink the sine and cos every time that you do this. Now we're going to apply this. Right, now on the next page, we are going to get the resultant, and now we're going to do a calculation. Now remember, you can do a scale drawing with head to tail or tail to tail to get a resultant, but that is time consuming and it is not always accurate, right? You have a thick pencil and you make a mistake of a few millimeters and that might be a few newtons, right? So this is much more accurate. And we're going to start by resolving the force into its components and then find the resultant of all the x components, then find the resultant of all the y components, and then we're going to use Pythagoras and the tangent to work out the magnitude and the direction. So let's start with this one. You've got two forces exerted on the same object, right? There's a force A, and that is a 50 Newton force in the direction 150. So if I just want to make a quick drawing, it's not to scale, of this, remember 150, I have to work from north and clockwise up to 150. Now remember, straight down to there would have been 180, so to have 150 over there, it means it will be something like this, right? And it's 90 up there, and then the rest 60 down there, right? Now, why do I try to get that 60? Because when I work out components, I always need the angle with the horizontal, right? So from the 150, I'm going to go with the 60. Right, so there I'm going to say this is FA, and I'm now going to replace that by the FA in the X direction and the FA in the Y direction. Right, so how do I work that out? Now FA in the X direction, remember for the X direction I'm going to use the whole force 50, and now for X I'm using cos 60. Just check that you have the angle with the horizontal. Right, and 50 cos 60, that ends up being 25, and remember you need two places after the comma, so right now start always checking that you've got two places after the comma. Right, and we're also going to work out the y component, and that y component will now be 50 sine of 60, and if you do that you end up with 43,30 Newton, and obviously that is south. Right, we took A and we split that up in the two separate components. Right, now we're taking B, and what we're going to do with B is exactly the same. Now B is in the direction 240 degrees, so let's think about this. If I start from north, it's going to be 90 over there, 180 over there, and if I reach that one, that would have been 270, right? So I'm going to stop short of that one. right? And I actually want the angle always with the horizontal. So let's think about this. Right up to there would have been 270. So if I want to stop at 240, it means the angle over there will be 30 degrees. Right. So now I'm taking that FB. I am replacing FB with an FB in the Y direction and an FB in the X direction. Right, so let's go and work that out. So FB in the X direction will be the whole 100, and I'm using cos for the X. I'm just making sure that I've got the angle with the horizontal, that 30 degrees. And then you end up with 86,60 Newton, and that is now towards the west. Right, and we're doing the same for the Y component. That will be 100 sine of 30, and you end up with 50. And remember, you're not allowed to write just that 0, 0, 2 places after the comma. Right, and that is also towards the south. Right, so now we have resolved the forces into components. Next up, we're going to get the resultant of all the Y components and of X components and the resultant of all the Y components. So let's look at the X component. So I've got 25 east and I've got 86,60 west. So west is definitely the one that is bigger. So for Rx, the resultant in the X direction, I'm going to use to the east, to the west as my positive. And that means I will end up with 86,60 minus that 25,00, and I end up with 61,60 Newton, and that is obviously now towards the west, right? So west is winning, right? 86,60 minus that 25. Let's do the same for Ry. Now the resultant in the Y component, now this component is down and that component is down as well. So definitely going to use down as positive, and that means I'm actually adding them together. So I have 43,30 plus 50. And that means I end up with 93,30 Newton, and that is now towards the south. So now I've resolved the force into components. I found the resultant of the components, and now I'm going to use Pythagoras and tan to get the direction and magnitude. So let's think about this. I've got an Rx towards the west. Now I like to use a tail to tail. So let's go and draw that. Rx will be towards the west, Ry towards the south. So I have them there, and then obviously, since they're tail to tail, I will complete the parallelogram. So I'm going to repeat that one on this side, right? So that is Rx as well. I'm just repeating it, and I'm going to repeat Ry on that side. Right, and then the diagonal is going to give me the resultant of all the forces. Now, since this is a 90-degree triangle, I can easily use Pythagoras. So r squared is going to be Rx squared plus Ry squared, and then I end up with 61,60 squared and 93,30 squared, and that gives me 111,80 Newton. Right, so there I have the magnitude. Now I still need the direction. Now if you think back, what do we do in science? Now remember, in science we're going to work from north clockwise. Right, so we started out with north over there, and we work clockwise up to our vector. Right, so if I want the direction of that vector, I need that angle. But first off, I will calculate this bottom one, and then I'll add it to 180. So I'm working with this angle. If I'm working with this angle, remember this one is going to be adjacent, that one is going to be opposite, and the final one would be hypotenuse, and we're not going to use that, right? So now tan theta will be, right, and that will be opposite, which is Rx, divided by Ry. So I end up with tan theta being 61,60 divided by 93,30. And then you have to work out the angle, right? Now remember to work inverse or second function, right? Tan of that answer. And if you do that, you end up with 33,43 degrees. But that's still not the answer, because that is just that angle down there, and we need the whole angle measured from north, right? So from north, the direction will be 180 plus that 33,43, and we end up with 213,43 degrees. So now we both have the magnitude and the direction. Right, guys, it's time for you to do a little exercise to see if you understand this, right? So on the next page, there's a 1.2, and at the bottom there's 1.3. You have to pause this video, do the questions, and then come back to see if you've got a good grasp of what you're supposed to do. The two forces are exerted on the same point as indicated in the diagram. Okay, over there they drew it head to tail, tail to tail, but we're not going to do a diagram. We're going to calculate the magnitude and also the direction of the two forces, the resultant of the two forces. So this one is already in the x direction, so I don't need to resolve this one in components, but this one I will need to replace with an FB in the y direction and an FB in the x direction. Right, so I'm going to replace this one. Okay, let's resolve. So what do I need? Now they give us the angle with the vertical. For me to use cos for the x, I need the angle with the horizontal. So I'm going to take 90 and take off 25, and I end up with 65 for that one. That will make it easy for me to know that the x component is going to be the whole force, 15 times cos 65, and I can use cos because I'm using the angle with the horizontal, right? And that's going to give me 6,34 Newton, and that is now towards the west. Right, doing the same for the y component. Now for the y component, that will be the whole force times sine, of 65 degrees. And if you do that, you end up with 13,59 newtons, and that will now be south. Right, so now I have all the components. Now I'm going to look at the resultant. Right, let's look at the resultant in the x direction. Now you've got in that direction, I've now worked out this is 6,34 Newton, and in that direction you've got 12. So obviously that is the bigger one. So I'm going to use to the right as my positive direction, and then that will be 12 is in the positive direction, and I add minus 6,34, which is in the negative direction. And if you do that, you end up with 5,66 Newton, and since it's a positive answer, that will now be in what direction did we choose as positive? Towards the east. Right. Next up, we're looking at the y components. Well, if there's only one y component, then that y component is going to be the resultant. So the resultant will be 13,59 newtons towards the south. Right, so now I have the resultants in the two directions, and I can add them together to get the final result. So now in the east direction, so in that direction, I'm going to have an Rx of 5,66 Newton, and towards the south, I'm going to have Ry, and that is going to be 13,59. Now I've used the tail to tail, so I have to complete the parallelogram and get the diagonal as my resultant. Right, now since this is a 90-degree triangle, I can say r squared is equal to rx squared plus ry squared, and that will be 5,66 squared now, plus 13,59 squared. And if you have that, remember to get the square root, right? And if you get the square root, you should end up with 14,72 newtons, right? Now that is the magnitude. Now we need the direction. Now let's look at this one. That is the starting point of my vector. So I'm going to measure from north clockwise up to my vector. So I'm going to first work out this one as my theta, and then I'm going to add the 90-degree angle there at the top. So let's work in this triangle because I'm looking for that one. So if I'm looking for that one, then the adjacent is going to be my 5,66, and my opposite is actually that RY that is repeated over there, RY of 13,59 Newton. Right. So when I do this, I'm going to work with tan. Right. So the tan of that angle that I'm looking for is opposite over adjacent. So that will be RY divided by RX. And RY, that was 13,59, and RX, that was 5,66. And then if you work out the angle, you should get 67,39 degrees. Right. Okay, guys, it's always worthwhile to just stop and see, is that possible? Now, if you think about this one is longer than that one, right? So that is going to be a very big angle. It's going to be bigger than half, right? So 67,39, that sounds to me quite possible, right? But still, that's not the direction I'm looking for. What is the direction I'm looking for? The direction must be from north clockwise, right? So the direction will be 90 plus that 67,39, and I end up with 157,39 degrees, right? So quite a long way to go. Resolve into components first, right? Then look at all the x components to get the answer for the x. Look at all the y components to get the answer for the y, and then get the answer of the answers. Right, easy enough. Right, let's look at the second question. Now here they tell you 3 charged spheres are placed as indicated in the diagram. The magnitude of the electrostatic force between them, between x and y, the magnitude is 2,4 millinewtons. Between x and z, the magnitude is 1,2 millinewtons. And now they calculate the net electrostatic force, and now most important, on x. So the others are going to experience net forces as well, but we're not asked. We're only asked to work out the net force on x. So the question is, what does x feel? Now, what is y going to do with x? They repel each other, but I'm not asked what's happening to y. I'm only asked what's x experiencing. So if they are pushing each other away, x will be experiencing a force to the left. So you will have f of y on x towards the left. Right, and then we're working with x and z. And what is z going to do with x? It's going to repel x. So it's going to push x upwards. So you will also have the force of z on x, and that is going to be an upward force. Right, and if you've got 2 and you're looking for the answer, now I've drawn them tail to tail. So I will have to complete the parallelogram and get the net force as the diagonal. Right, now for F net, since this is 90 degrees to 90-degree triangle, I'm going to use Pythagoras. So F net squared will be equal to, F y on x squared plus F z on x squared. Right, now what did they tell us? Y on x, 2,4, and just remember that little m there is millinewtons, so it's times 10 to the minus 3 to get to newtons, and remember to square. The other one is 1,2 times 10 to the minus 3 and squared, and remember to get the square root over there. And when you get that square root, you will end up with 2,68 times 10 to the minus 3 Newton. Now we have the magnitude. We still need the direction. Now when I work direction, remember we're measuring from north clockwise right up to our vector. Right, so you have one or two choices. You can work out that one and subtract from 360. Right, or you can work out the bottom one and add to 270. So which way do you want to go? Now, any which way. You could have gone one way or the other way. So let me work out that one. Now, for me to work out that one, that will be opposite, right? That is the y on x, and this one is going to be adjacent. So if I go with tan theta being opposite, if y on x divided by adjacent z on x, right? Now, y on x, that was the 2.4 times 10 to the minus 3, and z on x, that will be 1.2 times 10 to the minus 3, and then working out the angle. Right, so you have to work with second function tan of 2. Right, and that should give you 63,43 degrees. Right, is that the direction? No, that's just that angle. Right, so what I have to do to get the direction is going to be, let's think about this. I have that one, and I need from there right up there. So that will be 360 minus 63,43 degrees. Right, and that is going to give you 296,57 degrees. 296,57 degrees. So now we've worked out both the magnitude and the direction of the net force working on X.